Well, hi there, sports fans, and welcome to another exciting episode of Physics 12. Today we're looking at lesson 1.5, and the topic is free fall. Now, we use the term quite often, free fall, in various ways, and but you may not have thought about what does it really mean. What does free fall actually really mean? And so I've got this definition here for you, where free fall is defined as the state of an object when the only force acting on it is gravity. Now that may seem like a pretty straightforward statement, and it is. However, there are some tricky aspects to it which I will talk about in just a minute. So for example, the usual way that we use the term free fall is when somebody is skydiving. And this is when somebody jumps out of a perfectly good airplane. I'm not quite sure why a person would want to do such a thing, but people do that. And so oftentimes they will not deploy the parachute right away. They will just drop out of the plane and then open the chute after a period of time. That period of time is what you would call a free fall. And again, that's just because the only force acting on that person at that time is gravity. Now you have wind resistance as well, but we're not taking that into account at this time. What you might not have recognized is that a satellite is also actually in a free fall. When a satellite is orbiting the Earth, the only force that is acting on it is the force of the Earth's gravity, and so it also actually is in a state of free fall. And along with that, the International Space Station. And also the shuttles, the one that's docked to it, or when the shuttle is orbiting the Earth and it's not using its rocket engines, it also is in a free fall because the only force acting on it is the force of the Earth's gravity. So when the only force is gravity, then an object is in a free fall. And you might also not have recognized that an object could actually be moving up and still be in a free fall. So don't get fooled into thinking that something has to be falling to actually be in a free fall. And in that sense, it might not be the best term for something that the only force acting on it is gravity, because things may not necessarily be falling, yet they may be in a free fall. An example of this would be okay, so something could actually be rising and still be in a free fall. An example of this would be throwing an object up into the air. So if I were to toss this pen up into the air, as soon as it leaves my hand, the only force that's acting on it is the force of the Earth's gravity. And so as it's going up into the air, it technically is in a free fall. So as soon as it leaves my hand, I apply a force to it in order to accelerate it upwards. But while it's rising, the only force on it is gravity. So it's in a free fall. So while the pen is on its way up, it is indeed in a free fall, and then it stops at the top. Keep that in mind as well, is that the object will actually come to a stop at the top and then go back down again. Because we will make use of that information in just a little bit. So where we're heading with this is projectiles, and we will be leading into the topic of projectiles, which is quite comprehensive. But for now, we just want to focus on the free fall. And so, if you think about a projectile, whenever something is launched, it becomes what we call a projectile. So it doesn't matter what you launch it from, whether you launch it from a catapult or if you launch it from a bow. So let's say you fire an arrow from a bow. As soon as it leaves the bow, it's a projectile, and it's in free fall. Or for example, like a potato gun. As soon as you fire off that potato, it becomes a projectile, and it's in a free fall. The path that these objects will follow then is whatever it's launched from. Let's say it's launched at this particular angle right here, it'll follow that kind of a trajectory, and that's what we call projectile motion. This is in 2 dimensions, obviously. For now, we're just going to be looking in 1 dimension, but soon we'll get into 2-dimensional motion like this as well. And so this is the projectile motion actually follows what we call a parabolic type of a trajectory. So if you were to actually graph this would actually be a parabola. All right. So after launch, then the only force acting on it is gravity. So indeed, as soon as it's launched, then it becomes then it's in a free fall. Now let's look at an example of where we would use this kind of information. And so this is a bit of a tricky kind of a problem. So that's why I'm going to do this on the video for you at this time. So what we have is we have a person, they bend their knees 20 centimeters and they push on the ground, and then they push off the ground and they fly 50 centimeters into the air. And what we want to know is the speed at which they leave the ground, and they're accelerating during the push-off phase. So, I must apologize at this time for my artwork, or should I say, lack of artistic talent in being able to draw anything half decently. This is as good as it gets, stick people, so my apologies for that, but hopefully you recognize what's going on in this situation. So we have a person standing straight up, they bend their knees, and so they drop down 20 centimeters, and then they use their legs to force themselves in an upward direction. And here is the time when the person lifts off the ground, and then they end up moving or flying 50 centimeters into the air. So we're going to divide this up into two phases actually. So the push phase is the when the person has bent their knees for 20 centimeters and they use that time to push up off the ground. And then immediately when the person leaves the ground, then we call that the fly phase. So we have the push phase and we have the fly phase. Now it's a little tricky to think about exactly what's going on in these situations in terms of solving these kinds of problems. The best thing to do is probably to not worry about what's happening to the legs of the person, but just focus on the torso of the individual. If you focus just on this section of the person, then it's a little easier to deal with. So the first thing we're going to do is we want to find their speed when they leave the ground, and we're actually going to go to this phase first in order to determine that, because we have enough information here in order to be able to determine that. So let's see how we'll do that. So we want to find the initial velocity or the speed of the push-off as soon as they leave the ground. Now we know that, and as I mentioned earlier, when something is launched up into the air, at the top of their motion, their velocity is 0. So we can make use of that at this time in order to determine what their velocity is when they leave the ground, because we're going to use this equation right here. V final squared equals V initial squared plus 2AD. And you can see from this equation, we know everything from this equation except the initial velocity. So we use at the top of the motion, the velocity is indeed 0, so we put that number in there. And we can put the other numbers in there. The acceleration in each of these situations, the acceleration due to gravity is minus 9.8 meters per second squared. And I'm sure you've come across that before. So we can just put those numbers into the equation here, and I trust that you can do the algebra. And when you do, then you will get an answer of 3.13 meters per second. So we've just determined that the person had to have been going at 3.13 meters per second. That would have been their velocity as soon as they left the ground. And that would enable them to fly 50 centimeters or half a meter into the air. All right, so that's the first part. And then part B, we want to find their acceleration during the push phase. And as I mentioned, the best thing to do is to just think about the torso of the person here, and the movement of their torso. Don't worry so much about the legs, the knee bend, and that kind of thing. Just remember that if you focus on the torso, what's happening is the force is acting over 20 centimeters. So the person's torso is being accelerated in an upward direction for 20 centimeters. And that's the important thing to keep in mind. Now, we will use, again, the same formula to find out the acceleration. This acceleration now is not the acceleration due to gravity. This is the acceleration in order to allow the person to leave the ground at 3.13 meters per second. So we know everything from this equation right here. The only thing we don't know is the person's acceleration, so that's what we're solving for. Their final velocity, we just calculated that. So while they're accelerating, they leave the ground at 3.13 meters per second. So that's our final velocity now for the push phase. And don't get the initial and final velocities confused from the push phase to the fly phase. We're now in the push phase, so when they left the ground, that's the final velocity at the instant the person leaves the ground. So that was 3.13 meters per second, which we had just determined. And then we know all the other numbers. They start from a standstill, so the initial velocity was 0. Acceleration we don't know. And the distance that the person is accelerated for is 0.2 meters. And again, I trust that you can do the algebra, isolate A, and when you do, then the person was accelerated at 24.5 meters per second squared. Okay, so again, a bit of a tricky sort of a problem. You will come across these. And so, as I mentioned, the best way to think about it is in terms of just think about the torso of the person and what's happening with that as opposed to their leg movements in providing the force, etc. And we'll do some other, a couple of other examples in class with this. And for now, we will just be sticking with one dimension like we did right here. And then down the road, we will be looking at motion in 2 dimensions and as it pertains to projectiles.